Okay, good morning. We are going to continue with lecture number 9 in electric drives course. So in the last class, we had looked at current and voltage sensing. Before that, we had looked at speed sensing. Then we also discussed different types of controllers to control the current when you are operating a drive system. So in today's class, as I told you in the last lecture, at the end of last lecture, we are going to look at PLL based control, that is phase locked loop based control of electric drive. Okay. So what is a PLL? So the phase lock loop actually comes out as a single chip these days. So PLL consists of mainly 3 components, and PLLs are extensively used in electronic application to generate certain frequency waves so that we would be able to broadcast some kind of secretive signals through a particular frequency very accurately. So that it cannot be intercepted so easily by anybody else. So PLL consists of a phase detector, which is going to exactly find out the difference between the phases of two signals. So let me draw this. This is the phase detector. So I'm not showing exactly what this is, but basically this will be normally a multiplier unit. So this is phase detector. To the phase detector, you're going to give a particular frequency that is to be tracked by the output signal. So the error between these two input signals, one is the reference signal, the other one is the actual frequency what you're outputting. The difference between these two is detected by the phase detector. Now the phase detector goes to a filter. So the filter is going to filter out any of the high frequency components. So when you talk about multiplier, very clearly, if I have a omega 1t and omega 2t signal, we will have omega 1 minus omega 2 as one of the components and omega 1 plus omega 2 as one of the components. So if we are looking at omega 1 minus omega 2 when they are very close to each other, then this is going to come out as the phase difference. So if I put the low pass filter, this particular component will be eliminated completely. Only this will come out, which happens to be the phase difference. So the filter would generally be a low pass filter, and the output what comes out of this will be proportional to the phase difference between the two input signals. Now, the output of this filter will be given to a voltage controlled oscillator. So this is going to be a voltage controlled oscillator, VCO. So the voltage controlled oscillator, as the name indicates, will give out a frequency which is proportional to the input signal. So it is essentially whatever is the amplitude that is coming out here, that will be converted into corresponding frequency at the output. So this will be amplitude to frequency conversion. So this, what comes out here, this frequency is going to be proportional to the amplitude which is going into the voltage controlled oscillator or VCO. Now, the frequency that comes out will be again fed back to this particular input, one of the inputs of the phase detector. That is going to be the actual frequency, F act. So this is the basic working of PLL. So the voltage controlled oscillator will be continuously getting signals from the filter through the phase detector such that ultimately the frequency what is coming out here that will match with that of what is the reference frequency. The two will be exactly match with each other. So in this particular case, when we want to use this kind of a PLL for controlling the speed of a motor drive, what we are going to do is we are going to give a F star or reference depending upon what kind of encoder we are having. If we have a speed encoder, it is going to give out signals in a particular sequence depending upon the speed of this particular disc which is attached to the shaft of the motor. So this is essentially the encoder output. So the encoder output will be at a particular frequency for a particular speed. So if I want a particular speed, indirectly I should be able to give this is the reference speed I want to obtain, which will indirectly tell me what is the reference frequency that I need to get out of this encoder. So the encoder is going to decide basically what is the reference frequency or reference speed. Now I have the phase detector here. The phase detector and filter, both of them are going to do the same function as what it was doing in a normal PLL. Now all we are going to do is to replace this voltage controlled oscillator by a control circuit which is going to adjust the control signals to a converter. Now this converter is going to feed the motor, and the motor is of course coupled to the load. So motor is going to be coupled to the load, and we are going to have this motor also having an encoder. So I'm going to have basically an encoder which is connected to the motor. So this is coupled to an encoder. Now the encoder's output, what is coming out of the encoder depends upon the speed of the motor. So the encoder output is going to go as F actual to this phase detector. So the encoder will follow whatever is the frequency that is given as the reference frequency, which means any difference in the speed will immediately reflect in the output of the encoder. That is going to be adjusted as per the error that is coming out of the phase detector and the filter. So the control circuit will adjust the firing of the converter in such a manner that you are going to get ultimately the reference frequency matching with that of actual frequency, which means we are going to get the required speed. So the encoder will keep giving the speed signal in the form of frequency, and that frequency will be adjusted until it follows exactly whatever is F star. So this is really going to be a very, very accurate system for making sure that your motor drive outputs the required amount of speed, irrespective of load variation, irrespective of any other variation in the system. This encoder will always pass on the frequency, actual frequency signal. So the converter will adjust itself until F star and F actual are matched with each other, which means you have to get the actual speed itself from your system. Until then, it's going to adjust repeatedly. Okay. So until now, what we had been discussing about the drive system was its control aspect. What are all the different control configurations that can be utilized to achieve the required amount of torque and speed from a drive system? And we also looked at sensing aspects, how to sense voltage, how to sense current, how to sense speed, all these things we looked at. So based on this, I would like to work out one problem on encoder. So one numerical example on encoder. So I'm going to work out one numerical example on encoder. So the problem statement is as follows. An encoder has to be used for measuring speeds in the range of, so an encoder has to be used for measuring speeds in the range of 100 RPM to 3000 RPM. Okay. With its output pulses being counted for a duration of 100 milliseconds. The counter that is employed in this application has a maximum value of 4095. This is actually 2 power 12. So this is going to be a 12-bit counter. What is being employed is a 12-bit counter. Okay. The resolution, the speed resolution needed is 1 RPM. So we should be able to differentiate between 99 RPM and 100 RPM. So that's what we mean by resolution needed is 1 RPM. Okay. So how many holes need to be carved? How many holes need to be carved along the periphery of the encoder disk so that all the above conditions are satisfied. Okay, so this is what is being given as the problem. So let us try to see whether or how to work out the solution for this. Okay. So what we want to measure, the speed range that we need to measure, that is from 100 RPM to 3000 RPM. And what we are counting is, so the count is acquired for 100 milliseconds. So if a count is being acquired for 100 milliseconds and the maximum count is 4095. So the maximum number of counts will come out for 3000 RPM. When I have 3000 RPM as the speed, that is when I'm going to have the maximum count. So let us first of all check if it is 3000 RPM. 3000 RPM will correspond to how many revolutions in 100 milliseconds. So this will correspond to how many revolutions in 100 millisecond. First of all, let us try to get that. So I should say 3000 divided by 60 will give me revolutions per second or revolutions per 1000 millisecond. So 3000 divided by 600, right? So that is going to be 5 revolutions per 100 millisecond. And 5 revolutions per 100 millisecond should not exceed 4095 count. So let us try to look at if 4095 pulses are counted for 5 revolutions, then per 1 revolution, number of pulses will be equal to 4095 divided by 5. This is going to be the total number of pulses what you would get. So that is approximately equal to 819 pulses per, one revolution. So if there have to be 819 pulses, let's say there can be 819 holes on the periphery of the disk. So let us also check for 100 revolution per minute, how many pulses are going to come out. So for 100 RPM, we are going to have 1 by 100 divided by 600 because that's what we did. We divided by 600 to get how many revolutions per 100 millisecond. So this is going to be 1 by 6 revolutions per 100 millisecond if I am talking about 100 RPM speed. So I should be able to say 1 by 6 multiplied by 819 is going to be the number of pulses that come out of the encoder. So that corresponds to 819 divided by 6. So that will be approximately 136 pulses that will come out for 100 RPM. So if I want 1 RPM resolution, okay, so you can say that for maximum speed of 3000 RPM, we are getting totally 4095 pulses. That is the count that we are getting. And for 100 RPM, we are getting the pulses to be 136. So I should have for 1 RPM, it will be 136 divided by 100. So it will have 1.36 pulses. At any rate, it is greater than 1 at least. So this is going to be greater than 1 pulse. So this encoder should be able to give a resolution of 1 RPM and it will be able to measure from 100 RPM until 3000 RPM for this kind of given specification. In fact, we can have slightly less than 819 holes also, because if we have slightly less than 819 holes also, we will be able to get at least 1 pulse per 1 RPM. It's not a big deal at all. We should be able to do that. So the number of holes what we calculated as 819 would still work. There is no problem, absolutely. Okay, so that's what I was trying to say. Now we are going to migrate to the next chapter. This is going to be thermal calculations and selection of rating of motor for a particular drive application. Okay. So we are going to look at how we are going to calculate the temperature rise of a particular motor when it is driven at a particular rate or at a particular load torque and so on. So based on the thermal calculation, we would say if the motor is not getting overheated for this particular kind of load application, this rating of the motor will do the job. So that's what we are going to do. So if you look at any electric motor, its efficiency is generally good when it is operated close to its rated power. So we would like to select a motor such that it will be operated close to its rated power most of the time so that we get a good efficiency from the motor. Otherwise, we are going to waste a lot of energy that is being supplied in the form of heat losses, maybe copper losses, maybe constant losses, and so on. So we definitely need to calculate what is the kind of power output which will be expected of a motor, and then we'll try to make sure that we choose a motor whose power rating is close to the output power that it is going to deliver most of the time so that it operates at a good efficiency. So in this particular module, what we are going to really discuss in this lecture, we are going to mainly talk about three things. One is to get the temperature rise of the motor. How do we really get a thermal model for the motor? How are we going to develop a thermal model for the motor? That is the first thing. Second thing that we are going to look at is what are all the different types of loading in various applications that take place. So this we call as classes of duty. So we may be continuously loading a motor like a fan or pump. We may be just operating it at a particular power most of the times. Whereas if you look at an electric vehicle, you will start several times, you will stop several times. Sometimes you may overload, especially during starting. Then after that, the load can come down drastically. So you are going to see repeatedly the power fluctuating in the case of an electric vehicle motor. Now, third one is based on what kind of thermal capability the motor has and what kind of load it is going to be subjected to, how we are going to select a motor of a particular rating for a given application. So we are going to talk about all these three things in this particular module. And if you look at generally any electrical machine, the major two losses that we talk about are constant losses and copper losses. And copper losses are going to be normally variable losses. These are generally I square R losses. And constant losses could be in the form of core losses or magnetic losses, assuming that the machine is going to operate at a particular flux. Then you might have stray load losses, which cannot be really accounted for very systematically. And another one is mechanical losses, which is friction and windage losses. So these are all going to be there. We cannot say really friction windage loss is a constant, but depending upon what is the kind of speed variation you anticipate, this could be a constant or this could be a varying quantity. So these are the different types of losses we encounter. Out of this I square R losses really are going to be quite high, and these happen in the windings of the motor. And the windings are generally surrounded by insulator, and they are also placed inside slots. So they are not going to come in contact with any cool air which is surrounding the machine. So cooling the windings is going to be really, really difficult. So almost cooling the winding is next to impossible, I would say. So it is windings which are really going to be at the receiving end of having a huge amount of temperature rise. That is the reason why the insulators can get ruptured very easily. So the insulators can get ruptured due to two reasons. One could be due to the temperature rise itself, I square R losses themselves. And the second thing could be if I apply a very high voltage to the winding, then the insulator can get ruptured again because it will be breaking down against very high voltage. But while operating a drive, we are going to talk about I square R losses more and more, which means temperature rise more and more. So there are different classes of insulation that are there for many of the electrical machines whose windings are going to be fortified with this kind of insulator. So we have different classes of insulators like A, B, C, and then we are going to have E as one more, which is coming somewhere in between. This is going to be F, and this is going to be H. So the lowest class of insulator is generally called as gamma. It can only withstand about 90 degrees centigrade, nothing more than that. Whereas class A of insulation will be able to withstand 105 degrees centigrade. And this will be able to withstand, class E will be able to withstand about 120 degrees. So like this, as you go along, class C will be able to withstand slightly greater than 180 degrees centigrade. So all these things are differing from each other by about 10 or 15 degrees, nothing more than that. But the moment, for example, a machine which is having class E insulation for its winding, if the temperature becomes greater than 120 degree, immediately that insulation is going to rupture. So our goal should be to maintain that the temperature should be less than 120 degree even for the winding. So if we look at the entire machine as a lumped quantity, one single quantity, then in that one single entity, in that case, probably we will say that it is better not to exceed even 100 degrees or 105 degrees on the whole, because the external portion of the machine, if it is getting heated up to 100 degrees, the internal windings could easily heat it up to 120 degrees even in that situation. So we have to ensure that the insulators are protected and insulators are not going to be really getting overheated. So for this purpose, when we talk about the temperature rise, it's very, very important to develop a thermal model for the electric motor. So what we mean by thermal model for an electric motor is if we know the losses incurred inside an electrical machine or electric motor? Can we predict the temperature rise? This is what we want to know, whether we would be able to predict the temperature rise clearly. This is what we want to know. Okay. So for this purpose, we are going to look at the entire machine as one entity. What we mean is, although the windings are made of copper, the insulator is a different material, the core is made up of iron, we are not going to treat each of them separately because we are looking at the entire thing to estimate the temperature rise approximately. So what we do here is to estimate the temperature rise approximately. So we will not be able to make very, very accurate predictions, but this kind of estimate is good enough when we are trying to select a particular motor for a particular application. Okay, so let us try to first of all develop a thermal model for the machine. So we are going to assume as though a machine is like a cylinder. So this is the machine which is shown in the form of a cylinder. So from the surface area, we are going to see that the heat is going to get emitted. So the surface area, if it is larger, it will be able to emit more amount of heat from the surface area. That is the reason very often, if you look at the motor surface will always have some kind of fins. The fins are actually allowing you to have more amount of surface area. Let me try to show what is a fin. So fins on the surface of the motor. So let us try to look at some image. So you can see that this motor, if you look at it, it is not having a smooth surface. What you have is something like a groove, and it is actually having more and more amount of surface area because of the grooves that have been carved along the surface. You can see here also, this also has some grooves, so which is going to actually give additional surface area so that the cooling takes place very quickly. Okay, so let me come back here. So the surface area plays a very vital role in deciding how much of cooling would take place. But on either side, you might have coupling, and there could be other load mechanisms which are coupled very closely here. So in all probability, this area and this side will not be able to really provide any cooling at all. You may not be able to circulate any air, whereas we may be able to have a fan to blow cold air on the surface area here. So the fan would be able to cool the surface area much more easily in a motor. It is possible that it can cool more easily in the case of a motor. Okay, but even this is going to be pretty difficult when you talk about an electric vehicle or something, because this motor will be fixed somewhere underneath, so it may not be able to receive cold air very easily. So we can talk about natural cooling without really having any fan. So if there is no cooling arrangement, then we have to essentially look at some kind of natural cooling that is taking place in the motor. Otherwise, if we are really having some capability to provide some fan and there is space, in that case, you are going to provide additional cooling arrangement to ensure that the motor actually becomes cooler faster. Okay, so let us first of all look at various parameters that we are going to consider for the motor. Let us say the surface area of the motor, inclusive of fins and everything, let us say is A meter square. That is going to be the surface area. And let us say the emissivity of this material, what is used on the surface of the surface material, let's call that as lambda. So that is going to be lambda. So lambda is essentially going to be measured in terms of how many watts it is going to emit within, a short duration, and how many per meter square, how many watts per meter square. And as the temperature of the surface increases further and further, it is going to emit more and more amount of heat to the surrounding environment. So this is for degree centigrade difference in temperature with respect to surroundings. So if the temperature increases further and further, it will emit more and more. That is the way it is going to be. Okay. And let me call the losses in the machine to be P watts. The total losses in the machine I'm calling as P watts. Okay. Now I'm going to write the equation for a duration of dt seconds. So the losses in joules, if I try to write, I should be writing this as P times dt. Okay. Now, whatever are the losses incurred by the machine for the duration of dt, this heat energy is going to do two jobs. One is part of the heat energy is going to be dissipated using this emissivity. So from the surface area, the heat is going to be dissipated. And the second portion of this heat is going to go towards increasing the temperature of the machine's active parts. So what are participating really in working and also in, delivering the power to the load. So those portions temperature are going to increase. And the second portion is emission from the surface. So the total heat generated by the machine due to losses, those losses are going to be going to increase the temperature of the active parts of the machine, and part of it is also going to be emitted from the surface. So if we say that the machine's average specific heat capacity is going to be S. So that S is going to be again specified in joules per kg weight of this particular machine, and for increasing the temperature by 1 degree centigrade. So this is degree centigrade rise in temperature. Okay. So if we say this way, then we should be able to write this equation heat generated in the form of losses, that is going to be equal to P times dt. So this is going to be the heat generated by the machine for a duration of dt. And if I try to look at the temperature of the machine, how much it is increasing, I should say if the weight of the machine is W, and if S is the specific heat capacity of the machine, and if the temperature increases by d theta within a duration of dt, then that is going to be Ws d theta, where W is going to be the weight of the machine. Okay. Now, this is the portion which corresponds to the temperature rise, the heat which is going towards temperature rise. Then the last portion is what is being emitted from the surface, the heat that is emitted from the surface, that is going to be lambda multiplied by whatever is the area of the surface area of the machine. And let's say theta is the temperature difference between the ambient temperature and the machine's surface temperature. And this has to be multiplied by dt because we'll get only this in watts. And if I want to convert that into joules so that the equation is written in terms of heat energy, so I have to multiply that by dt. So this is the approximate equation that talks about temperature rise in a machine when the machine is having a loss of P watts. Okay, so I can just write this. Let me divide this by lambda A dt. Let me divide this entire equation by lambda A dt. So I should be able to write this as P divided by lambda A is equal to Ws divided by lambda A multiplied by d theta by dt plus theta. So this happens to be a first order differential equation that is describing the thermal behavior of this electrical machine. So this is an approximate equation that we have taken because we are not really talking about specific heat capacities of different portions of the machine. We are talking about the entire weight of the machine lumped into one single unit. So that is WkG. Specific heat capacity is going to be S. And even the surface material we are assuming is one single material that is being used on the surface. And that is actually lambda. See, one reason why many of the machines are painted black is to make sure that the heat is radiated very easily. Black bodies generally emit the heat very easily. So that is the reason many of the machines have fins. Many of the machines are painted black. Okay, to increase the emissivity of the machine. So now we are going to call this Ws by lambda A as heating time constant of the machine, which is going to be tau h. So this is going to be the heating time constant of the machine. So I can write this equation as tau h multiplied by d theta by dt plus theta is going to be equal to P by lambda A. So this is very, very similar to the normal first order differential equation what we get in RL circuit or RC circuit. So I should be able to write the solution for theta. So theta is going to be whatever is the steady state temperature rise we get, theta SS multiplied by 1 minus e power minus t by tau h. And if there had been any initial temperature rise, that will also be slowly going out in the form of, or it is the temperature will kind of allow some amount of emission of heat, which will also be governed by this exponent. Okay, So this is going to be the function which is describing the temperature rise. So here temperature rise at a time t, that is going to be given by theta of t. So this is the steady state temperature rise. So I'm going to ask you to compare this equation with L by R multiplied by di by dt plus I equal to VDC by R. It's extremely similar to that. So when we write I of t, we will be generally writing that as VDC divided by R multiplied by 1 minus e power t by tau. Tau is L by R. So it is going to be TR divided by L. Okay. And we are going to say if there is some initial current, that is going to be I initial multiplied by e power minus TR by L. So this is the kind of equation we normally see for the current. So I am essentially writing the temperature rise of the same form. So from here, I should be able to say that the steady state temperature rise itself will be P by lambda A. This is going to be the steady state temperature rise. Okay. And tau h, we already said tau h is going to be equal to Ws by lambda A. And if there had been an initial temperature rise, that will also be taken into consideration ultimately to give us what is the present temperature rise that is encountered by the machine. So this equation, what we have got in the form of temperature rise for the machine, this is a very, very important equation for us because this we will be using ultimately to know what is the kind of rating of the motor that we would be able to employ in a particular application. If we know roughly this is going to be the temperature rise of the machine, whether it will be able to withstand this kind of loading. So that's what we are going to check before we employ a motor for a particular application. So there are different classes of duty for an electrical machine. So what do we mean by classes of duty? The standards that are created in Indian Bureau of Indian Standards, they have specified what all are the different types of classes of duty or what kind of applications are generally seen in day to day. So the first and foremost thing is continuous duty. This is one of the easiest duty for which we would be able to calculate the motor rating very easily. So continuous duty basically refers to, I'm going to have, if I try to plot what is the time versus power drawn from the machine, this is going to be always a constant. So this is very clear that you are not going to have any fluctuation in the power that is drawn from the machine. So this is a pretty straightforward answer to this. What is the kind of motor rating that you will employ for this purpose? If I say this is P1 kilowatt, so it is a no-brainer to just say that you would be able to employ P1 kilowatt rating of the motor for this particular application. Typical examples are like fans or water pumping that is being done in a thermal power station. For example, for a boiler, the boiler feeder pump always will be on. It will be always pumping almost the same amount of water. So you would be always selecting a particular rating for the motor. So this is going to be the continuous duty. Then we may have the second one as short-term duty. Short-term duty. So short-term duty basically tells clearly from the name itself, you can make out that it is going to be on only for a very, very short while. Rest of the times it may be off. So in short-term duty, what we normally see is, let us say this is the time versus the power, whatever we are talking about. So the motor is going to be on for a very, very short while, and it is going to be off for a very, very long duration. It almost cools down to zero temperature rise. Until then, it is not turned on once again. So typical example for this particular system is mixer, what we use at home. We will not be using it for too long a period. We will just use it for a short while and turn it off, and then it will be off for a long time. Another typical example is hand drill. Hand drill, we are not going to really use it for too long. Once we drill a hole, we are going to do whatever we need to do further, and then after some time, we might use it once again. So this is typically short-term duty. Then the third one may be intermittent periodic duty. So intermittent periodic duty is going to be, I'm going to have actually my motor loaded for probably a for a large power output. And after that, it is going to be on no load. It is going to be idling for a long time. And again, I'm going to have a certain high loading. Then it is going to probably be idling for some time. And again, it will go for, a high load like this. So this is typically, I told you about bottling plant. So in a bottling plant, as the next bottle comes in, then you are going to have the bottle being corked or closed. So at that point, you have to apply a huge pressure. Then after that, it will be simply idling, waiting for the next bottle to come up. So this is going to happen in a periodic way. Another typical application is cutting machines. So you may cut one after another many sheets of steel or iron or something like that, or you may cut papers. So you will have one after another multiple papers coming up, and then you are going to have, cutting action. So only when it is doing the cutting action, it is going to be loaded. Otherwise, it will not be loaded. So another is pressing machines. Maybe you have multiple papers put together and you apply a glue in between and you make a cardboard out of it. So you may press all of them together. So again, when you press, you are going to apply load. Otherwise, you are not going to apply any load. So this is typically the third type of load, what you are talking about. Then we may have another one is intermittent periodic duty with starting. So this could be probably for hoists and things like that. You may just take it, you may lift a weight and you may take it up. And then after taking it up, you may come down and you might have to idle for some time. Again, you may start the hoist. So this may be done repeatedly. So the fourth type of application, what we are talking about is you will have a high starting current for some time. Then you will have heavy torque. Then it is going to keep quiet for some time. Again, you will have a high starting current and you will have a heavy torque and this will go on. So this could be every now and then if you have to start a motor. Okay, so this could be in a hoist. This could be even in some kind of short distance vehicle, like a road roller, which is actually going until the end. You might stop. Then again, you might have to come back to again apply the roller on the road already that is laid. So this can be with intermittent periodic duty with starting. The fifth one could be intermittent periodic duty with starting as well as stopping. So here you might have some amount of increase in the current here also. So you may have an increase in the current and you may have an increase in the current here also. So that will actually indicate during stopping again you will have to have a large current drawn. So I square R losses are going to be higher. Then you may have continuous duty with variable speed. So we may require different type of speed for different operations. So this could be for a lathe machine or it could be for winch mechanism. So we will have continuously certain amount of load torque demand, but we may require it at different values of speeds because of which the power can change also. So these are all the different classes of duty we may encounter. So Indian standards have specified multiple kind of classes of duty. Now that we have different classes of duty, the next thing that we need to look at is if I am given a particular type of class of duty along with rating, how am I going to select a particular motor rating for a particular application? So we will look at this in the